Pluto is a faraway and perplexing planet, which was once a member of our nearby planet group's planetary family. However, recent disturbing announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning revelation. They suggest that this cold world is on a potential collision course with Neptune. But how could this happen, and what might be the consequences of such an immense event? Are we witnessing an intriguing cosmic curiosity, or is there something more to this coming massive impact? Join us as we examine the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was downgraded to a dwarf planet largely due to its unusual orbit, remains a subject of interest and study in the astronomical community. As indicated by recent predictions by leading scientists, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a possible catastrophic collision between these two planets, which could pose a massive threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution. But the intrigue doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, differing greatly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its tilt, which is determined at 17 degrees to the ecliptic plane. The path Pluto follows is significantly steeper compared to the other planets. This tilt and eccentric shape add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's orbit. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, contrary to what we would expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers tried to figure out its strange path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its steep tilt and elliptical shape. The mystery grew with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of space mechanics. The three-body problem in space refers to calculating how three objects, like Pluto, Neptune, and the Sun, move and influence each other through gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. For Pluto, this problem shows how its path, Neptune's orbit, and the Sun's gravity all align in a complicated way. The terms AM/ML libration and extension libration, along with the VSK oscillation, are key components of this puzzle. According to astrophysicists, what keeps all planets in their orbits is AM/ML libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned no less than 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from intersecting. Extension libration, on the other hand, refers to the upward movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other large planet, it is positioned well above their orbital plane, adding another layer of protection against potential collisions. Another key aspect of the situation is the VSK oscillation, named after three scientists, Bond, Zippel, and F, who studied how objects move in space. It explains how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity, and how this pull influences their motion. For Pluto, the VSK helps us understand why its orbit around the Sun is so unusual. Although Pluto's path seems chaotic, this oscillation ensures that it moves smoothly for a long period of time. The VSK oscillation shows that even when things in space appear chaotic and irregular, certain patterns and laws maintain a degree of control. These factors help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or veer off course. The three-body problem helps us understand how these factors change based on how the space objects pull on each other. Studying this helps us learn more about Pluto, our solar system, and distant galaxies and their stars. Mathematical simulations in the late 1980s revealed that, despite these stabilizing properties, Pluto's orbit is actually volatile, with slight variations in starting conditions leading to massive changes over millennia. Nevertheless, these unique properties of Pluto's orbit have been shown to maintain stability over extraordinarily long time scales. In fact, tracking the disorder of Pluto's orbit has helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has a unique relationship with Pluto, in which for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This relationship helps maintain Pluto's orbit. However, Neptune is not alone in this. Jupiter's gravity also plays a significant role in stabilizing Pluto's orbit. In fact, Jupiter's gravity alone is strong enough to ensure Pluto remains on a steady path for a long time, possibly billions of years. It seems that Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely through space without encountering problems. These peculiarities are crucial in the broader context of the universe, ensuring the control and consistency of celestial bodies' movements. Without these factors, our solar system would be a far more chaotic and erratic place. Bodies like Pluto could collide with others or be ejected from their stable orbits, causing impacts on other celestial bodies. For Pluto, in particular, with discussions about its potential crash into Neptune in the future, understanding its orbit is essential. It gives us a clearer picture of the solar system's dynamic nature. Pluto's position illustrates how even the most seemingly unstable orbits can reach a state of equilibrium through the complex exchange of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the irregular nature of celestial bodies, and Pluto's orbit is a perfect example of this irregularity. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is vividly demonstrated in the case of Pluto. This means that even small variations in Pluto's position or speed can dramatically alter its long-term orbit. Using computational simulations has been incredibly helpful for scientists to figure out how Pluto moves in space. These simulations use sophisticated mathematics to model how Pluto and other space objects, like Neptune, influence each other through gravity. By changing tiny details in the simulations, astronomers can observe how even small shifts can have a huge impact on where Pluto ends up. In the late 1980s, these simulations revealed something really interesting about Pluto's orbit. Even though it has mechanisms like AM/ML and extension libration to keep it stable, its path can still be erratic and unpredictable. If you start with even a tiny difference in where Pluto is or how fast it's moving, its orbit can end up looking very different over many years. Yet, even with this chaos, Pluto's orbit remains stable over long periods, billions of years in fact. This means that Pluto's journey around the Sun has a certain order to it, even though it might seem chaotic at first glance. Predicting infinite events, especially when they involve turbulent orbits like Pluto's, presents enormous challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical simulations provide a reliable way to understand and predict the future behavior of celestial bodies, they also highlight the limitations of our predictive abilities. These models heavily depend on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or distortion can lead to vastly different outcomes, making accurate predictions a daunting task. Moreover, the turbulent nature of orbits like Pluto serves as a reminder of the ever-evolving and dynamic nature of the universe. While we've made great strides in understanding space, Pluto's case serves as a reminder that our knowledge of the universe is still limited. Understanding the gravitational influences of the giant planets on Pluto's orbit offers valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can significantly affect the stability and trajectory of other bodies within the system. So why are prominent astrophysicists just now raising concerns about a potential collision between Pluto and Neptune, despite all these complex forces working to prevent such an event? Neil deGrasse Tyson, a well-known astrophysicist and a key figure in popularizing cosmology, offers a unique perspective on the mysteries of our solar system, particularly the fascinating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, offers valuable insights into the evolving nature of celestial mechanics and the public's fascination with the unexplored realms of space. His stance on Pluto's renaming is rooted in the continually expanding knowledge of our solar system. He believes the renaming was a necessary step in our understanding of the true nature of Pluto's orbit and its place in the wider cosmos. Tyson's stance on Pluto's renaming is rooted in the continually expanding knowledge of our solar system. He believes the renaming was a necessary step in our understanding of the true nature of Pluto's orbit and its place in the wider cosmos. He also underscores the idea that as our tools and methods of observation improve, so too should our classifications and interpretations of celestial bodies. In his view, the decision to categorize Pluto as a dwarf planet is part of the natural progression of scientific discovery, reflecting a more accurate understanding of planetary science. While Tyson and other astrophysicists are concerned about the potential collision between Pluto and Neptune, they also acknowledge that the complexities of orbital mechanics have kept Pluto and Neptune in a relatively stable, non-colliding state for billions of years. However, with the increasing precision of simulations and our deepening understanding of space, scientists are beginning to foresee scenarios that were previously deemed unlikely, perhaps indicating a future where gravitational shifts or other unpredictable factors could alter this delicate balance. The possibility of Pluto and Neptune colliding in the distant future, while still highly improbable, serves as a reminder of the dynamic and constantly evolving nature of our solar system. The fact that the two planets' orbits intersect and yet have managed to avoid a catastrophic collision is a testament to the delicate interplay of gravitational forces at work. Even the most stable and predictable orbits, like those of the gas giants, can undergo subtle changes over time that might eventually impact smaller bodies like Pluto. Moreover, these discussions about Pluto's orbit and its relationship with Neptune highlight a broader theme in modern astrophysics: the ongoing search for knowledge about the stability and fate of our solar system. As technology advances, astronomers are increasingly able to track objects in space with incredible precision, allowing them to predict the movements of distant planets and dwarf planets more accurately. This not only provides a clearer picture of our own solar system's future, but also sheds light on the behavior of other planetary systems in the universe, enriching our understanding of cosmic evolution. Despite the potential for future changes, Pluto remains a fascinating object of study. It represents both the complexity of orbital dynamics and the challenges of predicting celestial events over long time scales. The idea of Pluto and Neptune potentially colliding, though remote, serves as a thought experiment, a way to push the boundaries of our understanding and explore the ways in which seemingly stable systems can evolve in surprising ways. In the end, the story of Pluto's orbit is not just about a distant dwarf planet in our solar system. It's a symbol of the ever-changing, sometimes chaotic nature of space. By studying Pluto and its interactions with Neptune and other planetary bodies, we gain a deeper appreciation for the intricate and sometimes unpredictable forces that govern the universe. While we may never be able to predict every twist and turn in the path of Pluto or any other celestial object, the pursuit of knowledge and the use of advanced tools and simulations will continue to expand our understanding of the cosmic forces that shape our world.